let us start this lecture 35 with a thought process from Isaac Asimov, who says that the saddest aspect of life right now is that science gathers knowledge faster than the society gathers wisdom. It is very important and also very critical. And let us recall what we learned in the last lecture. And last lecture basically we have looked at the analysis of turbofan engines, right, and then we looked at the parametric characteristics of the turbofan engines, and we have learnt that the bypass ratio and the fan pressure ratio, compressor pressure ratio plays a very important role, and by enhancing the bypass ratio we can reduce the TSFC. And very important thing that we have learned that whenever we take care of the losses, the TSFC goes on increasing for a particular fixed parameters, right, and whereas the specific thrust being reduced, and of course the propulsive efficiency gets enhanced, but the thermal efficiency reduced. So, overall efficiency basically reduced whenever you take care of losses in the analysis. Now, we will take up an example as usual to illustrate how we can solve this problem without really resorting to this parametric analysis, that means which is being carried out. We will be doing very systematic way, and which can be basically done by hand, not by using computers, and for computer you will have to use the equations which were derived for parametric analysis. A turbofan engine is flying at flight Mach number of 0.85 at an altitude of 10 kilometer. The pressure ratio across the compressor with the polytropic efficiency of 85% is 10, that means pressure ratio across the compressor is 10, but total pressure ratio will be dependent on what is the fan pressure. In this case the pressure ratio across the fan is 2. So, the total pressure due to the compression will be 20 in this example, that you keep in mind. And this fan has polytropic efficiency of 82%. At the combustion chamber exit temperature is 1600 Kelvin. The burner has an efficiency of 94% and total pressure ratio 0.95. That means 5% losses will be there in pressure, total pressure in the combustion chamber. The bypass ratio of the turbofan is 5. We have taken in this example 2 separate conversion nozzle with the same isentropy efficiency of 95% is used to produce the thrust. Here it is given the same isentropic efficiency for the both nozzle, but need not to be, and it is not mixed together. There might be turbofan engine where it will be mixed and expanded in a single nozzle, right, which I have not taken in your this thing, but however it may be required to solve look at these things from your side. The mechanical efficiency of this engine assumed to be 95%, total pressure recovery factor in air intake is 0.91. We need to determine the specific thrust, specific fuel consumption, propulsive efficiency, thermal efficiency, overall efficiency. Of course, one can find out under the static condition what it would be these values, right, if it consumes 150 kg of second. I think the first part we will look at it, and second part I will leave as an assignment kind of thing. The first part means whenever it is at the flight Mach number 0.8 we will be considering that. So, of course, those values of the gamma g and gamma a is given. Keep in mind this gamma z what we will be using is 1.333 or it is not 1.3, right, what I mentioned here. These are the conditions which I want to skip basically, and if you look at bypass ratio 0.5 and at the altitude 10 kilometer, T naught is 223.3 Kelvin, P naught is 26.5, pi c is 10, and these are the values which you are given. I have just jotted down, and what we will do basically we will have to find out total thrust, right. Total thrust, if you look at it, is the m dot c, that is the mass flow rate through the core of the engines which is passing through, B9 minus B0 plus A9 multiplied by P9 minus P0, the pressure difference across the, plus that is for the fan, this is again m dot f into V9 minus B0 plus A19 into P19 minus P0, right. So, what we will do, we will have to basically find out the flight what you call velocity. What it would be, V0 will be can be easily determined because we know the temperature T0, we know the Mach number. So, V0 will be gamma, this will be gamma A R T0 into Mach number. So, all these values are given to you, you can get substitute these values and you will get 254.6 meter per second, right. And for isentropic flow, we know that Tt2 is equal to Tt0, right. Keep in mind this air intake, we are not adding any work or nor some heat is going out. So, therefore, the temperature remain constant and Tt0 can be related to T0 in terms of Mach number, and which we know very well, and substitute these values of Mach number gamma A, you will get these values. So, of course, the pressure we can get Pt0 by P0 for an isentropic flow can be related to Tt0 by T0 power to the gamma A divided by gamma A minus 1, and you substitute those values, you will get 1.6, it happens to be. This is due to what? Due to the ram pressure basically, right, because of it is coming, and then you are saying if it will attain the stagnation state, what it would be the pressure ratio, right, total pressure to the static pressure. So, we let us just keep this in mind. These are the turbofan schematic with the station number 0, 2, and of course, there is a 13 for the fan and 19 for the fan, that is the nozzle, and station 3 to 4 is combustion chamber. Of course, 2 to 3 in the case of core engine is the compressor, and 4 to 5 your turbine, and 5 to 9 nozzle, but actually nozzle will start from here, that is 7. But we are saying that station 5 is same as the station condition, that means properties like total pressure, total temperature is remaining same, but in real situation it will not be, right. But in this, even in the real cycle, we are considering that. So, if you look at the processes 0 to Tt2, it is in the air intake, and from 2 to 3 is your compressor, and 3 to 4 is your combustion chamber, and 4 to 5 the turbine, both the high pressure and low pressure turbine, and 5 to 9 is your nozzle. And this is of course for the fan engine, right, this is fan engine, and this 0 to 2 is your air intake, and 2 to 3 is your fan, and 13 to 19, this point is 19 basically, that is your fan nozzle. So, you should keep this station number, because as you go along we will be solving and using this station number. So, as the PRF, pressure recovery factor, in the air intake nozzle is 0.9, we can very easily find out total pressure ratio at station 2, that is PT2 by PT0, and this is nothing but your PRF, which is 0.91, and PT0 by P0 already we have determined, that is 1.6, and P0 of course we know from the altitude, that is 26.5, and when you substitute these values and get that, you will get PT2 as 38.6 kilopascals. Here what we are doing, each point we are solving, sometimes you may find it is not required, okay, but particularly real cycle it will be very essential. But in ideal cycle you can skip some of the calculations if you use it intelligently, but in real cycle it will be little tricky, for fan stream, the pressure ratio across the fan, that is phi f, becomes, it is straightforward, that is Pt 13 by Pt 2, right, and that is given as 2. So, you can get directly Pt 13 because this is known, right, Pt 2 is known, already you have evaluated. So, you can get directly Pt 13, and we can estimate the temperature at the station 13 by assuming that T 19 is same as that 13. Okay. I mean, of course, this is and is T 13 by T T 2 will be again P 13 by P T 2, and this is what you call fan pressure ratio is given P T 13 by P T 2, that is nothing but your 2. Polytropic efficiency we are not considering, we will have to consider that for the fan we need to consider the polytropic efficiency, right, P f, right, we need to consider that. And when we will substitute these values, you will get as T 13 is equal to 324.56, and critical pressure ratio across the nozzle can be determined as, because we need to find out whether it is a critical or not. Keep in mind, we are assuming that the nozzle is a conversion nozzle, because generally in the turbofan engine nobody really uses a conversion diversion nozzle because it is not required, right, and mostly it will be flying at not only the subsonic flow, but in case of even fighter aircraft people are using nowadays turbofan engine with very low bypass ratio, right, not high bypass ratio of 5 generally it is being used for the long range passenger aircraft, where which will be moving at in the level flight of 0.8, my flight Mach number of 0.85 generally around 0.85 kind of, but here we are assuming the nozzle to be a conversion nozzle, right, and that assumption I had not mentioned, but whenever you are doing you need to, it is not given in the problem, am I right. So, therefore, we need to assume that, right, and critical pressure ratio across the nozzle can be determined by P T 13 by P c, and of course, the nozzle efficiency is given and gamma z is given, right, 1.333, and then you can find out it happens to be 1.92. We had seen in the turbojet also, like these values, if your efficiency is 0.95 you will get that, otherwise it will be little bit smaller values or higher values depending upon the efficiency of the nozzle. So, now we need to find out what will be the pressure ratio, P T 13 by P T naught, right. So, the actual pressure ratio across the fan nozzle with respect to ambient pressure will be P T 13 by P T P c or P naught, you can say, this is basically naught you can say. So, that will be 2.91, that what is the meaning then? That means the pressure ratio across this will be higher. If it is higher, then is it choked or unchoked? It is basically choked. So, if it is choked, that means it is having a critical velocity. What is that? That is equal to the speed of sound at the exit. So, the static temperature at the nozzle exit can be determined very easily, that is because Mach number is 1. So, from that condition you will get T 19 is equal to T c 2 divided by gamma a plus 1 T T 5. Keep in mind that we are using here gamma a, right, but there what I have used is basically could have been used the gamma a as well, because we are not adding any heat, right. So, therefore, that correction has to be made, but and then you will get 213 Kelvin, right, 2 divided by 1.4 plus 1 255.56, that is 213 Kelvin. You got my point there in that. So, the static pressure at the nozzle exit P 9 becomes P 19 by P c, and P c by P T 13 we have already evaluated. So, you will get the P 19 as 40.2. That means, the P 19 is not same as that of the your what you call ambient pressure, which happens to be 26.5 kilopascal, but now it is 40.2 kilopascals. So, by using the equation of state, density of gas at the nozzle exit can be determined, because you use the equation of state and then find out, because you know P 19, you know T 19, and then substitute those values and you will get this thing, right. And similarly, we can find out V 19, which is same as that of the speed of the sound, and that is here again this will be gamma A, right, RTC, right. You will put 1.4, 287, 213, and that is 292.54. If you substitute these values, you will get. So, by knowing this, I can find out A 19 by m dot f, which is very easily from the continuity equation, we can get this, and that is nothing but 1 over rho 19 by V 19. You will just substitute these values, you will get this 5.2 10 into 10 power to minus 3 meter square second per kg. And the specific thrust with respect to total mass flow rate contributed by the fan can be evaluated as, because we know that TSF is alpha divided by alpha plus 1, alpha is your bypass ratio, which is nothing but your what, alpha is equal to 5 in this case. You will substitute values, you know V 19 we have evaluated, V naught we have evaluated, this portion we have also evaluated, and this is with respect to f, right. We have already evaluated, this is P 19 by P naught. So, if you look at P 19 we know and P naught we know, because P 19 is higher than the P naught in this case. So, when you substitute these values, you will get the 31.67 Newton second per kg. I think this will be kilo Newton per second kg. So, the total pressure ratio across at the station 3 is given by PT 3 by PT 2, which is 20, right, because why we have taken this 10 into 2, that is the fan pressure ratio, therefore, we have taken it as a 20, right, that you keep in mind. So, PT 3 will become P 20 into 38.61, because we already determined what will be PT 2, right. So, you can get that. Using the polytropic efficiency of compression, let us now evaluate this TT 3 by TT 2 into PT 3 by PT 2, eta minus 1, eta P gamma minus 1 divided by gamma A and eta PC. So, when you substitute these values, you will get 2.74, and then from that we know TT 2. So, you can get TT 3 as 700.02 Kelvin. By carrying out energy balance across the combustor, we can find out expression for fuel air ratio. I mean, we have already done this thing, we know all those values. TT 4 we know, that is given, TT 3 already evaluated, and delta S is given, eta B is given. So, all you substitute and get that values F, that is fuel air ratio. So, as the pressure ratio across the combustion chamber is 0.95. So, you can get basically PT 3 is pi B is your 0.95 into PT 4, no PT 3 this will be PT 3. Now, PT 4 will be basically pi V into PT 3, because pi V is what, PT 4 by PT 3 station number. If you look at combustion chamber, right, it is 3 and this is your 4. So, pi B will be PT 4 by PT 3. So, PT 3 is equal to pi V into PT 3, right, 0.95 into 772, that will be little lower than the PT 3, that is 733.4 kilopascal. So, we look at turbine, the total temperature at the exit of turbine is to be evaluated. We know that the function of turbine is to supply the requisite power to the compression and the fan. So, we can write down that the compressor work plus fan work will be supplied by the turbine. and there is an efficiency, mechanical efficiency, which will be always lower than the 1. So, if you write in terms of temperature and Cp like enthalpy change, then you will arrive at this relationship Tt5 is equal to Tt4 minus Cpa divided by Cpg eta m 1 plus f, then T33 minus Tt2 alpha Tt13 minus Tt2, right, that is Tt2. So, when you substitute these values, you will get as 892.84, because all these things we know, I mean Cpg, eta m, f already we have evaluated, Tt3 is evaluated, Tt13 is evaluated, this is evaluated, this is evaluated. So, you just substitute and those values. So, Pt5 by Pt4 we can evaluate using the again isentropic for the what you call the turbine, and we will substitute these values and get this number. So, by this we can find out Pt5 as the 50.6 kilopascal. So, now for nozzle we need to determine the critical pressure ratio across the nozzle, and we will do the similar thing. We will find it is happens to be 1.914, and keep in mind here we will have to use gamma g because it is a hot, right. So, therefore, we will have to use the gamma g, and in case of a fan we will be using gamma a, that is 1.4, and the actual pressure ratio across the nozzle will be Pt5 by P naught, which is 1.9. If you look at this ratio is less than that of the critical pressure, right. Of course, it is very little. If you look at that way, it will be almost critical, right. Okay. So, therefore, one has to be little careful in doing, because the situation will change, but in this case we will consider that nozzle is not choked, because Pt5 by P naught less than Pt5 by Pc, and then if it is not choked, P9 is equal to P naught, that means nozzle is fully expanded. So, we can evaluate this thing, and we using this 2 eta n Cp Tt5 1 minus P9 by Pt5 gamma z divided by gamma g, right, for the nozzle, right. So, by we know these values Tt5, we know this P9, Pt5, Cp, this will be Cpg, okay, eta n, all those things we know. So, if you look at I am using eta Cpg 1148 into 892.84, then you will get this 5939 meter per second. The specific thrust for the core stream we can evaluate, because there is no contribution of thrust due to the pressure, right. So, it is only due to the momentum, and you will get that the specific thrust for the core engine is 50 Newton per second. I think my hunch is that it will be kilonewtons, because it is it looks to me. So, you will have to cross check that. The total specific thrust of the turbo engine can be estimated as Ts plus this thing, that is you just add and you get this number 81.67 kilonewton per second per kg. It looks to me like that. So, TSFC can be evaluated as TSFC f divided by Ts 0.029 divided 81.67, you will get 355.1 milligram per Newton per second. So, we can evaluate the propulsive efficiencies, right, and substitute these values, and you will get the same thing what we had done. Keep in mind that this propulsive efficiency 73.92, which is happens to be quite a bit high, of course, the thermal efficiency being reduced. So, is a smaller values. So, with this we will stop over, and we will discuss this maybe if you are having doubt little later on, and now we will move into the turboprop engine. So, if you look at turboprop engines, which is having we have already discussed in the ideal cycle, it is having a propeller, having a compressor, which and then combustion chamber, that is the high pressure turbine, and low pressure turbine is connected to the propeller through a gearbox, right. and most of the thrust is being obtained by the propeller and small portion is being obtained by expanding gas in the nozzle. Generally conversion nozzle is being used, and the processes will be similar to the turbojet engine, only difference would be here, that in this portion, that is the expansion in the high pressure turbine. This is high pressure turbine, and low pressure turbine will be much higher as compared to the nozzle. Nozzle is very small, that you should keep in mind, right, and rest of the things is similar to that of the turbojet engine or the core engine of the what you call turbofan engine. So, what we will do, we will basically look at the similar expressions, I mean which we have already done. This for the core, right, engines, we are not considering the propeller part, and which you will recognize these are the similar terms. I am like V9 by A naught and flight Mach number, and then T9 by T naught we have, which you have already seen, and V9 by A naught, and these are the terms which we are very familiar with. Let me not spend time on this. From the definition of a work output coefficient for the core stream, one can really get the T C V naught divided by the m dot C and C P and T naught, right. So, if you look at, you can get an expression like this, you can derive it very easily. We had done similar thing in the case of your ideal cycle, except this term is due to the pressure thrust, which is the extra, because here nozzle is not fully expanded, right. Therefore, this term is extra, which will be similar to that what we had done earlier for case of turbojet engine or turbofan engine. So, the expression for V9 by V9 by A naught will be similar, but only terms what you will get here, we have separated it as tau Th and tau Tl. Instead of that, we generally use as tau T, right. We never really separate this high pressure and low pressure turbine temperature ratio. That is the only difference, rest of the things are fine, and this you keep in mind, this will be I guess Vz minus 1. So, the carrying out the energy balance for the main combustor in the core engine, we will get the similar expression as I have shown here, like which is same for both turbofan, turboprop, turbo jet engines. So, we need not to really do anything, but this is the very important part, we must look at it, because the energy balance between high pressure turbine and the compressor, and also we will be looking at the energy balance between the low pressure turbine and propeller. So, if you look at W dot C is nothing but eta m h into W T h, right, and you can write down m dot A C P A, and this m dot A we also write this as m dot C, keep in mind, right, okay. M dot A, this A is equal to m dot C, what we use. So, you should not get confused, and multiplied by T T 3 minus T T 2 eta m h m dot f plus m dot f m dot A plus m dot f into C P z T T 4 minus T T 4.5, keep in mind this is very important point, this is for the high pressure turbine. So, when you do that, and where eta m h is the mechanical efficient high pressure shaft, when you simplify it and express in terms of temperature ratio, you will get as tau T h is equal to 1 minus 1 over eta m h 1 plus f tau r divided by tau lambda multiplied by tau c minus 1, right. So, if you look at, this is the same as that of the what you are getting for the turbo jet engine or the core engine of the turbofan, there is nothing much difference. Only thing is that in place of this we are using the tau h here, there it will be tau t. This is in this case turboprop engine tau t h, and we know that power consumed by propeller is equal to power supplied by low pressure turbine. With this we can write down this power consumed by the propeller is equal to eta G B, this is the gearbox efficiency, eta ml, that is the mechanical efficiency of the low what you call pressure turbine shaft, right, and m dot 4.5 Cpg Tt 4.5 minus Tt 4, and when you do little manipulations and you will get basically this expression. How you will get, like I can divide it by this is as Tt 4.5 and this is Tt 4.5 and that is 1, right. And if you look at this is nothing but your tau T L, right, and when I divide this I need to multiply it by here 4.5, yes or no, right. So, and then this expression Tt 4.5 and Cpz I can express in terms of tau lambda Cpa T naught and tau Th. I am just leaving it because if you look at the by definition what is lambda? Lambda is equal to Cpz Tt 4 divided by Cpa T naught, yes or no, right. And in place of Tt 4 let me just do little bit and then leave it Tt 4 by Tt 4.5 Tt 4.5 divided by T naught, and this is what is this one? This is nothing but your tau T h. Is it tau T h or 1 over tau T h? That is 1 over tau T h, yes or no. By definition Tt 4.5 divided by Tt 4 is tau T h, right. So, therefore, it will be 1 over tau T h and you will do that, you will get these values. I will leave it here for you to look at it. So, now we will look at this coefficient of the propeller. So, that is C propeller. If you look at eta propeller, W dot propeller and divide by m dot C Cpa T naught, and we have already looked at that eta W dot propeller will be eta Gv and eta ml m dot 4.5 Cpa T naught tau Th tau lambda 1 minus tau Tl, that we have already looked at. If you divide it you will get basically what you are doing, you are basically multiplying this substituting these values here, right. When you substitute then Cpta you will cancel it out here, m dot 4.5 by m dot C is nothing but 1 plus f. So, that is why it is coming over here, right, and the rest of the things are as usual. So, if you look at this C propeller we can express in terms of this. So, hence the total the coefficient of the power will be equal to C prop plus Cc, and then total specific thrust and work out coefficient becomes basically T s is equal to T divided by m dot C, and this is C total Cpa and T naught divided by V naught. So, expression of specific power will be W dot total divided by m dot C. Keep in mind that all the time in case of turboprop engine we are multiplying by the dividing by the mass flow rate through the core engine. So, that is nothing but C total Cpa and T naught. So, let us derive an expression for TSFC and PSFC. So, TSFC will be F into V naught divided by C total Cpa T naught, and this is same as that what we had done for the ideal engine, right, ideal cycle analysis. So, PSFC will be a similar thing, only difference the m dot f divided by the power produced by the specific power produced by the engine total, right. So, that will be C total Cpa and T naught, f divided by C total Cpa and T naught. So, thermal efficiency will be as usual, and keep in mind that this thermal efficiency we have evaluated in real cycle without considering the pressure effect, right. Okay. So, that you should keep in mind, and the overall efficiency will be basically W total divided by m f delta S c, and keep in mind that propulsive efficiency you will get by determining the overall efficiency and thermal efficiency in case of turboprop engine, right. But in case of turbojet and turboprop we get directly. So, that is the only difference you should keep in mind so far efficiency is concerned, the rest of the efficiency are similar. Now, we will carry out a basically parametric analysis and see what we are getting. What we are doing here, we are taking this tau t as various values like your 0.6, 0.7 and 0.83, and if you look at these curves like is corresponding to the specific thrust which is plotted on the left hand side, and here of course the pressure ratio across compression. You can see that this the solid line is corresponding to the real cycle and dashed line corresponding to the ideal cycle, and in this case specific thrust goes on increases with the fan pressure ratio, have a peak values, and then it goes on decreasing, right. And in the case of ideal cycle it is having similar nature, but only thing is that in the case of real cycle you are getting the lower values most of the pressure ratio range across the compression. Of course, in some places it is going up and above the ideal cycles, but and as you go on increasing this temperature ratio across the turbine, right, it is a turbine, okay. This is the turbine. So, you will find that the specific thrust decreases. What is the meaning of that? Because the temperature ratio across the turbine is increasing, means what? It is other way around, that means expansion in the turbine is low, right, because this is 1 minus 0.8, it will be 0.2% what it will be, expansion will be there. That means temperature ratio will be other way around, because it is defined in the opposite, downstream divided by the upstream of a component, right, that always we define. So, therefore, it is a smaller value means expansion is low, higher values means expansion is more, right. So, the specific thrust will be decreasing, and of course, if you look at TSFC which is just opposite, that is 0.8 values, the tau t of 0.8, the specific thrust specific fuel consumption, it decreases and attains a minimum values, and then again it increases for the real cycle, and similar thing you will get in case of an ideal. Only difference between this real case and ideal case is that real case will have a higher TSFC for a particular values of pressure ratio. For example, if I take 10, then you will get these values of much higher, and if I put these values, this will be much lower. So, right. So, therefore, you will get a higher thrust specific fuel consumption due to losses, which is obvious case, and as of course, the tau t goes on decreases, you will get a lower TSFC, which is usual, expected. And if you look at the CC, like core engines, like you will find that CC is basically decreasing, right, as it is with the pi pressure ratio, it that CC it goes on increasing and reaches a certain values at the higher pressure ratio across the compression. And the real case, as I told, it is a solid line, is having a lower value as compared to the ideal one, which is a dashed line for a particular condition. And of course, as it is decreases, that is in this one basically tau t is equal to 0.8, and similarly this is tau t is equal to 0.7, and this is tau t is 0.6, right. And which is expected because the losses will be more. So, therefore, you will expect to have a work output coefficient will be lower in case of a real cycle, right, for a particular pressure ratio, a particular turbine temperature ratio. And of course, the C propeller, that is, it is decreases with increase in pressure ratio across the compression, and this is having a higher value as compared to ideal cycle, right, because the fan which will be taking the more amount of work, and then it will be higher than that. So, of course, this is for tau t is equal to 0.7, and this is for the tau t is equal to 0.8. So, it is if you look at other way around, you will get a fan pressure ratio which will be higher. So, what we look at is advanced turboprop engines, because of fact that this propeller cannot really operate at a very high speed, that is the one limitation. Or in other around, if you look at the turboprop engine cannot really fly at a high Mach number. For a particular RPM of the engines, when you fly, then what will happen? It will be having a very higher blade. So, then the blade tip will attain a local velocity having a speed more than the speed of sound. Then the shock will be formed, and then you will have several other problems. So, the losses will be very much higher, right. And in order to overcome that thing, what people are thinking about, that why not reduce the length of the blade and use the more number of blades, because number of blades less, then the work transferred to the momentum transferred to the air for getting thrust will be reduced, right. But if it is other way, if you increase, then you are getting a higher efficiency of transferring the momentum, so that you will get higher thrust. So, that was the idea which people try to do that, and then they felt that they will have to use a very highly swept blades, right. When you do that, then now as a result, so that you can fly at a higher Mach number, right, that is one advantages, and also you can have a higher thrust, right, because your static thrust should be much higher in case of turboprop engine. So, that is the advantages. So, they come up with ideas of a more number of blades. They experimented with the 8 number of blades, generally 3-4 people use 8 number of blades which have a much higher, but these are highly swept vanes, right. And these highly swept vanes can be operated at a higher RPM as well, because when you reduce this speed, then the gearbox will have very big, because suppose your engine is operated at 50,000 RPM, you will have to bring to 2000 RPM, right. It will be gear ratio of 25:1. So, the gearbox will be much higher, because the power level of the engine will be very high. In this case, not like your automobile engine, some few kilowatt, it will be order of megawatt, right. So, therefore, when you reduce the RPM to lower, then you will be reducing the gearbox weight as well. So, but the problem with this kind of vanes, it creates a lot of noise, right. And of course, to and it will be also give a offset kind of twisting, right, because that is known as the P factor. Asymmetric thrust will be generated when propeller rotate, it will create a asymmetric thrust. So, here it will be more stringent. So, in order to overcome that thing, they put a way, of course, this is a static kind of things one can think of, but there is another concept which was being used known as unducted fan engines, right. But if you want, like if you look at this, these are the vents, you can make it contra rotating. That means, if it is rotating in a clockwise, the other will be anti-clockwise, right. Then what you will get out of it? You will overcome the problem of the asymmetric thrust, and it will be more efficient, because the air is moving through the blade and it is going and it is a west. So, you will not get the thrust, because it will be having a swivel component. So, what you will give is the axial component will give you the thrust. So, therefore, in this case you will avoid doing that. That means, at the if there is a two what you call stages of blade or two rows of blade, then like, and it is rotating other opposite direction. So, then you can get a higher thrust. So, people have got around 6 to 16% higher in the thrust, right, using this, but however it is not being used in practical situation. People are saying that the gearbox is a problem, because you will have to transfer the what you call the power from the low pressure turbine to the propeller with the help of a gearbox, right, which is propeller generally in the front, right, as you see it is in the front. But then why not you attach this propeller to the turbine itself, right, instead of using a gearbox. We can directly do that and rotate at a little higher RPM, right, which is same as that of the low pressure turbine, right. So, that was the idea which people use, that is unducted fan engines, right. If you look at they directly with the turbine, it is attached the blades, right, there are, and which are counter rotating, right. It will be one in the clockwise direction, the maybe let us say first one, and second one will be the counter clockwise direction. So, they could manage to get a higher thrust and overcome the problem of the gearbox, right. Weight will be reduced, the efficiency, but it is having a problem. Problem is that noise is very high, and there is another problem of leakage, right. The leakage of this gas, hot gas, is another biggest problem. So, therefore, of course, the G has have developed this engine quite some time back, and they use a very highly swept vane as well, you can see, but it is not being used in practice, but however maybe in future it will be used. And we will be looking at the rocket engines in the next class onwards, and I will stop over